Okay, then let's move on to the next speaker, which is José Baggio. José Baggio is principal investigator in the Department of Language and Literature of the Norwegian University of Science and Technology in Trondheim. There is also heading the language acquisition and language processing lab. And José has worked on meaning composition, among others, both formally and neurobiologically. He has summarized his theoretical view and empirical work in a wonderful book, Meaning in the Brain, that's published by MIT Press in 2018. I can highly recommend this book. Today's talk has the title, Parallel Processing Architecture for Language in the Brain. José, the floor is yours.
Thanks, Peter. Let me see if I can share my screen. Okay, you should be able to see my slides now. And so thanks again for the invitation, Peter, and for organizing yet another wonderful event. It's too bad that we cannot celebrate the MPI at the MPI, but it's still nice, I think, that we can reach so many more people through a Zoom webinar. So what I'll do today is to present some ideas, really, and also some research results about the functional organization of what we call core components of language in the brain, so meaning and grammar. And I am going to argue that architectures are going to be important in the future to understand the complexity of language in light of the complexity of the brain, but also to begin to reintegrate the language sciences. But I want to take a step back and start really by introducing the capacity that we want to explain, or that some of us want to explain, mindful of what Vittoria has just said. So language understanding. So this is clearly a key capacity of our mind and brain, which we use habitually, including at this very moment, if all goes well. So it is a constructive process in the sense that meaning is not extracted from the input, but it has to be internally generated. So Andrea Moro has put it, I think, very clearly when he writes, what is crawling under your eyes right now has a meaning only because your brains are built to comprehend these sentences as instructions to produce meaning, not because meaning resides in the sentences. But what is meaning? I like to think of meaning as models following the tradition in formal semantics, at least to some extent. And models are internal representations of what is said, tracking salient, relevant aspects of reality in the service of thought and action, including communicative action, of course. Now, for example, suppose you are at a friend's place and they tell you, if there are no glasses in the cupboard, they are still in the sink. Now, here you might construct one model, one internal representation of this situation in which the glasses are in the cupboard, and then you only need to take them out and say, put them on the table for dinner. And another model in which the glasses are in the sink, and then you would perhaps need to wash them before you put them on the table. Now, these different models between which we are juggling actually allow you to reason about the current situation and also to plan your actions, your responses in it. We are slowly starting to figure out where models live in cortical space in the brain. And in this fMRI study, for example, we asked where complex logical propositions are represented in the brain. So we had participants learn associations between sets of arbitrary visual cues and propositions of the form P and Q, P or Q, and if P, then Q. So classical propositional calculus material, where P and Q were statements about shapes, like there is a yellow square and there is a green circle. Now, in the scanner, participants had first to recall a proposition when they saw the visual cue, And they had to maintain that proposition during a 6-second delay. Now, during the delay period, and here we use decoding, so we could decode cortical activity specific to each logical form, so the conjunctions, disjunctions, and conditionals, only in one region, the left posterior inferior frontal gyrus, so PIFG, which was the only area that contained information about the logical form of the rule maintained throughout the delay. Whereas other regions, for example, visual cortex, as you see in the maps here, encoded information only in some of the early time bits. So immediately after the delay period, participants had to evaluate the recalled logical proposition against a given visual target with actual shapes, actual colored shapes. And now this is the latest point in time at which they can construct meaning. Now they really have to do it. So they have to build models of the situation. And in this case, so in the evaluation phase, we found peaks of activation in the left anterior inferior frontal gyrus, so AIFG, so that's BA 47 and 45, and in and around the intraparietal sulcus, IPS. Now, in this frontoparietal network, activation was greater for disjunctions or and conditionals, if then relative to conjunctions. So both or and if then can be true in more ways than the conjunction and, which is true in just one case, if and only if both conjuncts P and Q are true. So the different ways in which or and if then can be true, the different models that make them true, seem to drive activation in this frontoparietal network. And IPS here is particularly interesting, I think, because it's been implicated in representations of sets and their numerosities, as well as representations of space and time. So it plausibly supports the kind of representations that result from language understanding in support of thought and action. Now, we are interested in how language understanding unfolds and how it works, and not just in where models are represented and maintained in the brain. And to correctly formulate how questions, in this case about language understanding, we have to look at it through the lens of certain important ideas in linguistics. And one of them is compositionality. So it turns out, and I think that's a pretty obvious fact, that we have a capacity to assign multiple meanings to the same expressions in natural language. And only some of these meanings are compositional, so strictly a function of lexical meanings or constituent meanings and the syntax. For example, a sentence like one here, he is really on the ropes now, has an idiomatic meaning that the subject, he is in a difficult situation, and a compositional meaning that he is literally on the ropes, if, say, we're talking about a fighter or a boxer. Similarly, the intended meaning of two, the first person landed on the moon in 1969, is that the first person to land on the moon did so in 1969, and yet the compositional meaning here is a bit different, namely that the first person in the universe of discourse, whoever that is, landed on the moon in 1969. So likewise in 3, the intended meaning of the first case of AIDS was reported in 1975, is that the first reported case of AIDS was reported in 1975. And this is quite difficult to derive compositionally, because as far as I know, there is no syntactic theory that allows you to interpret reported twice. So first covertly as a modifier in the subject noun phrase, and then again overtly in the predicate VP. And the compositional meaning here is that the first case of AIDS ever was reported in 1975, which is clearly not the intended meaning. So these are all examples by Pelletier in a 1994 Topoi paper, where he lists a great number of examples that, according to him, challenge compositionality. So compositionality then can be seen as the hypothesis that there is an exclusively syntactic and lexical root to sentence level semantic content, as the philosopher of language Emma Borg has put it. But I believe a full consideration of our capacity for understanding language actually shows that we need to assume two roots, or at least two roots. So one which computes meaning indeed compositionally, so strictly based on lexical or constituent meanings and syntax, and another root which uses different principles. So principles of an autonomous semantics. So here I'm following Kulikova and Jackendorf, at least in terminology. So an autonomous semantics that operates according to independent principles, so principles that do not track one by one syntactic operations, and that still is capable to recovering contextually appropriate meanings. So this is the idea behind the theory that I'm currently thinking about and developing. So the theory is, or includes, an architecture for language processing that comprises two parallel streams, what I call a grammar stream, or G stream, and a meaning stream, or M stream. I will not give a full detailed account of the theory here, but I'm going to show, at least in brief outline, a computational implementation in a minute. So this is how the system works in brief. So for every new input I, and you can think of this as a morpheme, a word, or some other unit of language, lexical information L is activated and is used by each stream independently to update intermediate stream-specific representations. And these are a representation of syntactic structure. I call this S in the G stream. So you can think of this as a syntactic tree or a constituency graph or a dependency graph, and in the M stream, an intermediate representation of a relational structure R. So this would be a semantic parse or some other kind of representation of semantic relations between words or whatever the input elements are. So these syntactic and relational structures, so these intermediate representations, are then used to update the current discourse model M. And this process is iterated incrementally at every new input. But the important point here is that not all iterations are equal. So in general, both streams will be active and will participate in processing, but the balance between them may change depending on a number of factors. For example, processing will favor the G stream when the input is a function word or a closed class word, or when the input's logical complexity or syntactic complexity increases. So in those cases, grammatical information tied to specific morphemes or words will be activated from the lexicon, will be used to expand the syntactic representation S, and then to update the model M, in this case, following the constraints as required by compositionality. Now, processing will instead favor the M stream if the input is a content or an open class word, or, for example, in the presence of rich linguistic or non-linguistic context. Now, in those cases, relational semantic information about, for example, plausible semantic relations between words or constituents, phrases, will be activated from the lexicon and will be used to update the relational structure and then the current discourse model M according to autonomous principles of semantic interpretation. And these will only have a weak or perhaps no correspondence at all with what happens in the G stream, so with strictly syntactic operations. Now, it is the shifting balance between the two streams that begins to explain our capacity to assign compositional and non-compositional meanings to the same expressions in language. Now, this balance is typically set by the system internally, depending on the inputs it gets, for example, but it is to some extent under voluntary control. So we could, for example, decide to pursue a fully G-stream compositional analysis of a given sentence and see what models it gives us. And presumably this is what linguists do when they look at their examples, or alternatively, we could decide to pursue a plausible semantic analysis and then an interpretation through the M stream, even if that means that we would ignore some syntactic constraints. So recall the examples in the previous slides, and I'm going to give one more in a minute. So the basic properties of the model are autonomy and parallelism of the two streams, redundancy, or perhaps the right word here is degeneracy. So the idea that the two streams can actually compute some of the same outputs. And finally, integration of information coming out from each stream at the level of the discourse model. So our version of the parallel architecture seems plausible given general knowledge from neuroscience. So parallelism and redundancy are clearly two important principles of neural computation representation. But it is also plausible given what is known about language processing in the brain. So each processing stage in the parallel architecture can be put into correspondence with one of the four main ERP components that are known to be modulated by linguistic stimuli. So the LAN, the N400, the P600, and the SAN, which is sometimes referred to as the NREF. Now, this correspondence allows us to explain, at least in the context of the parallel architecture, why there are two successive grammar-related ERP components, the LAN and the P600, and two successive meaning-related ERP components, the N400 and the SAN, and why there is temporal overlap across streams between the two earlier components, the LAN and the N400, and between the two later components, the P600 and the SAN. Now, in what follows, I will first present an algorithmic implementation of the parallel architecture that is designed to explain an important, widely discussed data point in the neurolinguistics literature, which is the P600 semantic attraction effect. And then I'll move on to an empirical prediction that the architecture makes, namely that the P600 is actually one signature in the domain of ERPs of syntax-driven meaning composition, of compositional processing. And I will describe ERP results that indeed seem to associate the P600 to meaning composition in the G stream. Next, I will describe an EEG experiment of meaning composition across streams, providing some initial empirical information about how the two streams divide processing labor beyond the tentative guesses I made in the previous slide. And finally, I will present developmental evidence of parallel processing of meaning and grammar, presenting preliminary results from an EEG study in children at the age of 2. Okay, but let's start with the algorithmic model. So in this study, we had a simple goal, which is to provide what we call a computational proof of concept of the parallel architecture. So that is, we want to show that the parallel architecture can be given an algorithmic level implementation that actually works, specifically one that provides an explicit computational explanation of a known experimental finding, in this case, the P600 semantic attraction effect. So what is it? So semantic attraction effects have been described in the literature in a series of very interesting papers that started with, among others, the publication of a JML paper in 2005 by Albert Kim and Lee Osterhout, where they analyzed ERP responses at the main verb in what they call attraction violations, so sentences like "the bubble gum had been chewing," compared to both passive controls and active controls, like "the bubble gum had been chewed" and "the bubble gum had been chewing." Sorry, "the hungry dog had been chewing," so that's the active control. Now, all these sentences are syntactically correct in the sense that they will be generated or licensed by any grammar or parser on the market. It's just that attraction violations seem to be semantically or perhaps pragmatically off. So bubblegum does not chew, it's being chewed. Now, but when Kim and Osterod looked at ERP responses, so comparing attraction violations to either passive or active control sentences, they did not find any of the ERP effects that are commonly associated with semantics or pragmatics, so the N400 or post N400 negativities. So they found instead a known ERP signature of syntactic processing, or what at the time was believed to be an ERP signature of syntactic processing, namely the P600 effect. Now, one possibility here is that such syntactically correct sentences are nonetheless costly for the grammar system. So intuitively, the system could recover meaning based on known associations between words, between content words in this case. And the resulting interpretation, so the resulting plausible interpretation in this case would be that the bubble gum had been chewed, but this is in conflict with the actual form of the input string, which would then be perceived by the system as being ungrammatical. So the P600 here would not be a pure index of bottom-up syntactic processing, but rather a manifestation of conflict between the output of concurrent processes in the M stream and in the G stream. So our model was designed to capture this conflict in a bit more precise terms. So we implemented the parallel architecture in this single one-off version of the model, which works as follows. So it uses both off-the-shelf and custom-made NLP tools. So the G stream is shown in green here. It's a syntax module, which is essentially an incremental dependency parser. And to model the M stream, we used either a neural network or a probabilistic guesser. So these two systems do the same thing. They perform the same task, but they use different training data. So we could also compare their performance. So the syntax module is a standalone parser, as I mentioned, that requires no training. So it already returns a full dependency graph for any sentence of English that it gets as input. Instead, our model of the M stream had to be trained in order to produce outputs that can be compared to those of the G stream. So recall that we want to model the P600 effect, the P600 attraction effect, as a conflict between the outputs of the two streams. And since the parser produces label dependency graphs, so with labels for grammatical subjects, objects, and so on, so we want our semantics module to do the same, only based just on semantic information. So concretely, we wanted to produce likely labels of a verb's nominal arguments for bubblegum given chewed, based on what it has learned about bubblegum chewing and so on in an actual corpus of sentences. So the meaning module in our model had access to 3 sources of information, but to no syntactic information at all. So it had access to WordNet synsets, which capture conceptual semantic relations between lemmas. It had access to named entities, which specify whether nouns and proper names refer to persons, times, locations. And it had access to word embedding information, so containing distributional vectors in this case. And the probabilistic guesser was instead trained on only synsets, and the neural network on all 3. So the meaning module was trained on sentences from Wikipedia, and the error detection system, which is shown in red here, which is the system that detects conflicts between the labels as assigned by the parser and by the neural network or the guesser, was trained on 2/3 of the Kim and Osterhout corpus, so the actual sentences that they used in the ERP study, and was tested on the remaining 1/3. So the task was classification. So the system had to learn to distinguish attraction violations from active controls, passive controls, and no attraction violations. So no attraction violations are standard semantic violations that were not part of Kim and Osterhout's original experiment, but which we added as a further term of comparison. So here are some examples of output representations. So on top of each sentence, you see the complete dependency graph given by the parser over the output of the G stream. And below each sentence, you see labeled arcs, which would be the labels guessed by the M stream module based on the semantic information that it had access to during training. Now, in the attraction violation, the meaning module guesses that bubble gum should be the object of chewing. So note that it's making this guess only based on the associations that it has learned between these words. But according to the parser, this is not right. This is not what the input string actually says. Bubblegum is the subject of this sentence. So there is a conflict between the two labels. So subject coming from the G stream and object coming from the M stream. And that is why the system learns to classify this as an attraction violation. Now, instead, the labels produced by the two modules in the passive control and in the active control conditions are consistent. So the meaning module makes correct guesses that the G stream approves, so to speak. So in the no attraction violation, the meaning module simply encounters a combination of a verb and argument that it has never seen before. So it cannot label the arc between chewing and meeting in this case, so it's unknown. So the model achieves decent classification performance in spite of the fact that the training corpus from Kim and Osterhout was fairly small, so 384 sentences, and that the test set was even smaller, 128. So if you compare these numbers to the huge numbers that you see in the NLP literature, you'll agree with me that these are small numbers. But most sentences in each case are correctly classified. And if you look at attraction violations, we find that the neural network seems to outperform the probabilistic guesser, but the difference is quite small. So this shows that synsет information, which is all the probabilistic guesser had access to, seems to be enough to perform the task, and that distributional information, which only the neural network gets, in addition to synsets and named entities, only results in marginal gains. All in all, this is proof that the parallel architecture, at least in this very first tentative implementation, works. So it classifies sentences pretty much the way the brain classifies them, distinguishing attraction violations from both active and passive controls and from no attraction violations. So it also provides a possible first step to a plausible algorithmic level account of the P600 effect as observed by Kim and Osterhout, if the explanation that it reflects a conflict in the concurrent assignment of subject and object labels by autonomous meaning and grammar streams is on the right track. Now, the theory also implies that P600 reflects another type of interaction between meaning and grammar. So the theory says that the P600 is elicited when there are two types of interactions going on between syntax and semantics. One, which is what we just saw, when the meaning constructed by the M stream has conflicting implications at the level of syntactic structure in the G stream. And this is the process that corresponds to the dotted backward going arrow in my cartoon here between M and S. And this kind of interaction is revealed, among other things, by semantic attraction effects. But there is another type of interaction between syntax and semantics, which is the situation where meanings are composed from lexical items or syntactic constituents as compositionality requires. So here the theory predicts, again, P600 effects. And note that this is not a trivial prediction. So syntax-driven meaning composition is, if anything, the opposite kind of interaction between syntax and semantics than the one revealed by semantic attraction. So it would be surprising and indeed informative if this prediction were confirmed. Now, there have been only a few attempts at studying syntax-driven meaning composition using EEG or MEG, but most of that work has followed what I think is a valid three-step strategy in experimental design and implementation. So it's work we can trust. So first, minimize context by using phrases instead of full sentences or discourse. Second, find ways of minimizing the role of stored knowledge of semantic relations, precisely to avoid semantic attraction type effects or other effects driven by world knowledge, plausible thematic relations, and so on. And third, to use appropriate non-composition baseline and controls. And this is the hard part of this game. Now, there is a line of research, a very productive and interesting line of research using MEG, which is led by Leena Pilkanen at NYU, which unfortunately I cannot review here, that has indicated that syntax-driven meaning composition is, for several reasons, difficult to find in the brain. So in her own words, theoretical linguistics posits syntactic and logical semantic composition as the main combinatory routines, but the most consistent and prominent reflection of composition, so this is the effect that they describe in many of their MEG papers, localized in the left anterior temporal cortex at 200, 250 millions, cannot be described with this toolkit. There are many reasons why this is the case, but one is that this effect seems sensitive to conceptual relations between words. For example, the specificity of nouns in combination with adjectives. And this is exactly the kind of relationship between words that syntax-driven composition should not be sensitive to, if you believe the linguists' theories of composition. But the question remains whether any other components in MEG or EEG might reflect syntax-driven meaning composition. So our theory predicts that one of these components is the P600, and we decided to test this prediction by using a design that follows as much as possible the three-point strategy just described. And we also use stimuli as in the majority of Pilkanen studies, namely noun phrases. So all our noun phrases add the form determiner adjective noun, and as in all our experiments, the stimuli are in Norwegian. So in this experiment has a non-semantic baseline, so we use non-words, so letter strings that are not possible Norwegian words, and pseudo words, which are not actual Norwegian words, but obey the phonological and morphological rules or constraints of Norwegian. So like trådisk here. So we included inflection and agreement between the pseudo adjective and the noun. And in the semantic conditions, which are the full conditions you see below the non-word and the pseudo word here, we used real adjectives instead. So in this particular study, which was the first in the series, we used modal and temporal, privative and non-privative adjectives like an acte president, a real president, and nåværende president, a current president, and falsk president, a false president, and en tidligere president, a former president. So the noun, as you can see, was the same in all conditions, so that we could compare EP responses to lexically identical nouns across different prenominal contexts. And the composition contrast theories between all four semantic conditions collapsed, where the meaning of the noun can be composed with that of the adjective, and the two non-semantic conditions, so the non-word and the pseudo-word, where the meaning of the noun may be indeed activated, but it cannot be composed because the pronominal stimulus carries no meaning. So we found the P600 for this contrast. And we could also show that the different types of adjectives did actually not impact the P600, which is what we expect from a neural signature of syntax-driven composition. So in this study, intentionality, the contrast between modal and temporal adjectives, and denotation, the contrast between privative and non-privative adjectives, modulated respectively the N400 and post N400 negativities, so both M stream processes. So we are now trying to replicate and extend these results using other classes of adjectives in the semantic conditions like intersective, subsective, anomalous adjectives, and also different pre-nominal stimuli than non-words and pseudo-words in the non-semantic conditions, such as sub-modifiers. So these are adverbs that would modify an adjective that, however, in our stimuli is not there, so leading to composition failure. So far we replicated this P600 effect in 3 studies using these different pre-nominal modifiers. So we have seen that the theory can explain and predict known and novel instances of the P600 in terms of 2 different types of syntax semantics interactions involved in the G stream. So I will now look at other ways in which the parallel architecture allows for the construction of meaning. Now, according to the theory, composition can actually happen in a number of different ways in both streams. So there is no single mode of composition. So syntax-driven composition in the G stream, which is what we discussed so far, is just one of them. So we have started a new series of studies using a new experimental paradigm where we try to understand how the brain breaks down the problem of meaning composition in real time, and how the M stream and the G stream divide composition labor. In this line of work, we used full sentences instead of phrases. And as we will see, the ERP data show that in sentence context, the brain responds rapidly to stimuli that require composition in the earlier time frame in both streams, where the LAM and the N400 are modulated. So we developed a new experimental paradigm that allows direct comparisons of identical sequences of 2 words in contexts that require the 2 words to be composed, what we call the composed condition, versus contexts in which those same 2 words are separated by a natural syntactic boundary, what we call the cut condition. So in this first study, we constructed cut and compose conditions in 2 different syntactic environments, in noun phrases and in verb phrases. So our participants read cut sentences in which the adjective and noun, in this case, bråkete, noisy, and music, belong to 2 different clauses. So to translate, construction sites are noisy, music can be relaxing. And they also read composed sentences where the same adjective and noun in the exact same sequence now had to be composed. So on construction sites is played noisy music on the radio. And we had a similar composition contrast in verb phrases. So in cut sentences, a verb and a noun, so here hörer, hears, and music belong to 2 different clauses. So noise is sometimes something one hears. Music is nice. And in contrast, in composed sentences, the same verb and noun, again in the same sequence, could be composed together. So noise is tiring, but someone hears music among all sounds. Now, with these sentence pairs, we can actually isolate the brain responses under line composition by comparing directly the compose versus the cut conditions in each environment. But we can also ask whether composition responses will differ between noun phrases, so B versus A, and verb phrases, so D versus C. So in all four conditions, the earpiece signal is time-locked to the onset of the noun, which is here Musik. And with this paradigm, we can begin to address questions of how the two systems divide composition labor. And at the same time, we can start providing data that's also relevant for answering questions that are independent of the parallel architecture. For example, there are long-standing discussions in formal syntax and semantics on whether to explain linguistic structure and meaning we need several compositions or rather a single universal composition. For example, linguists have modeled the composition of a verb and an argument, such as hörer Musik, by using merge at the level of syntax and functional application in the lambda calculus at the level of logical semantics. And the discussion has been whether one needs distinct operations for modifiers and modified elements, such as an adjective and a noun, like brokete Musik. For example, a join instead of merge, and predicate modification instead of functional application. And it's interesting to note that one finds the same questions in current statistical approaches to language and meaning, for example, in distributional semantics. So whether the network or the machine learning system that you're using has to learn one or several composition functions. So in the cut minus compose contrast, we found that composition has different effects on the ERP in noun phrases and verb phrases. So here, the top row shows plots of the for the NP condition of ERP effects, so compose minus cut in all channels. The overlaid ERP waveforms in just one channel, CZ, a statistical heat map of ERP effects across times and channels, and a raster plot which shows the time channels pairs that belong to the highest ranked statistical cluster. So composition in NPs, so composing a noun following an adjective, results in a reduction of the N for 100 at the noun, whereas composition in verb phrases, so composing a noun following a verb, results in an increase of the LAN again at the noun. Now, these effects have opposite sign and different spatial distributions. So with the N for 100 reduction being stronger on central and posterior channels, and the LAN increase being stronger on frontal channels. But there is also temporal overlap between the two. So they both happen in roughly the same 250 millisecond window. Now, this result is not predicted, of course, by the parallel architecture, and perhaps it is not even readily explained by it, but it's the start of a more systematic investigation on what kinds of linguistic structures would be preferentially processed by the N stream or by the G stream. It also suggests that linguistic theories that posit a single universal operation in syntax or semantics may have their own good reasons to do that, but they will eventually be more difficult to reconcile with neural data once their algorithmic and neural implementation is being evaluated. So the last study I want to present is part of an ongoing longitudinal project in which we follow the development of lexical and compositional semantics in infants from 9 to 22 months. And at 22 months, we sought evidence for parallel processing of meaning and grammar, again, using ERPs. So this is the study that I will briefly describe now. So let me just say that developmental data are an important source of evidence for the theory. And the reason is that meaning grammar parallelism should, if the theory is right, be an intrinsic property of the human mind. So it should not be a byproduct of, say, explicit language instruction or metalinguistic awareness, or even strategies that adult participants use to perform a laboratory task under time pressure. Now, meaning grammar parallelism should just be the way the language system works at early stages of development as well as later in life. So discounting neurological conditions, of course. Now, obviously, development happens, so we do not expect the exact same organization in infants and adults. So we expect to see a degree of parallelism in how infants at a certain stage of maturation of the system process meaning and grammar in spoken language. It also turns out that language development itself provides arguments, at least for the relative autonomy of semantics from syntax. So compositionality, or better syntax-driven meaning composition, does not quite explain the fact that most infants can understand simple multi-word utterances even before core elements of grammar or syntax are acquired. So it must be possible for infants to compose, to construct meanings in ways that do not strictly rely on grammar. Because indeed that capacity, the capacity for representing syntactic structure, is not yet fully developed. Now, EEG research supports, to some extent, the meaning before grammar view of language acquisition. So ERP data show that infants are sensitive to lexical semantic relations between words or other perceptual stimuli starting at six months of age, and that at 18 months, they show enforanded effects to semantically incongruent words in sentences. Sensitivity to morphology and syntax appears only later. It's reflected in ERPs only between 18 and 32 months of age. So what's most important for our purposes is that, according to the ERP literature, the end of the second year might be a good age to test early manifestations of meaning grammar parallelism. So around age 2, most children are reported by parents to be combining words, and they are presumably able to be to compose meanings in both receptive and productive language, which is an indication that the parallel architecture might then be in place. So we tested Norwegian children at 22 months of age. So here's a participant in our lab. So they are listening to spoken phrases in Norwegian, played through a pair of loudspeakers, while unrelated images, so attention grabbers, are popping up on the screen. So in this study, they listened to noun phrases, so determiner, adjective, noun, and to verb phrases, so verb, determiner, noun, in which all verbs were transitive, all nouns were singular, and all determiners were indefinites. So we manipulated lexical semantic congruency between the adjective and the noun, which is S here, and between the verb and the noun. So congruent combinations are rö and äpple, so red and apple for NPs, and spise and äpple, eat, and apple for VPs. Incongruent combinations would be blå and äpple, blue and apple, and drikke and äpple, drink and apple for VPs. So we also manipulated morphological gender agreement of the determiners, the adjectives, and the nouns. So here, for example, äpple is neuter, so it requires both the neutral form of the determiner et and the neuter form of the adjective rødt or blått with the T suffix. So we expect that Norwegian children at 22 months of age are sensitive to lexical semantic incongruencies and to morphological agreement errors. And that's what we found. So for lexical semantic incongruencies, we see a clear enforanded effect at the noun, which shows a posterior distribution and latency similar to the adult enforanded. And we then looked at the effects of morphology, so agreement errors in NPs. And we found a different effects, in this case, an anterior positivity. So yellow color here in the heat map indicates a statistical cluster with a positive sign. And finally, we also analyzed ERPs elicited by nouns across VPs and NPs. And we observed, again, a positive effect with a frontal distribution. So children at 22 months of age are sensitive to semantic relations in context, to morphological gender agreement, and also to the syntactic context of composition. So the temporal overlap between these effects is consistent with parallel processing. So some conclusions. I like to think that the future of a scientific field, whatever it is really, is shaped by new emerging questions, as well as old questions that do not go away. So these are questions that remain at the center of discussion in spite of other advances in research. And I've suggested that compositionality is one example of old questions that do not go away, and another is computational architectures. So architectures are right now central in theoretical linguistics, in psycholinguistics, in the neurobiology of language, as it's becoming clear also in computational linguistics, NLP, and AI. So parallelism and redundancy are pervasive at all levels of the organization of neural systems. They are part of a story of how brains achieve their remarkable speed and their efficiency and their robustness. And I believe that they are also at the core of language. And that's what I meant when I said at the start of my talk that we need to understand the complexity of language in light of and in terms of the complexity of the brain. So meaning grammar parallelism has never been a particularly prominent or visible mainstream position in linguistics, but at the same time, parallel architectures are never far from the mainstream. So I agree with what Ray Jackendorf says here, that elements of a parallel architecture have actually been implicit in practice in the field. And here, I think he's referring to generative linguistics for years. And this is actually the case in formal semantics as well. So if we look inside one of the classic texts of this field, so Hyman Kratzer's Formal Semantics in Generative Grammar, so we find statements that seem quite surprising, at least to me, like this one. So we are adopting a view of grammar as the whole, on which syntax and semantics are independent modules. So they probably would never endorse a parallel architecture of the kind that I sketched in my talk, but I think that recognizing the respective autonomy of modules for syntax and semantics, not just the autonomy of syntax, is an important, clear step in that direction. So in this talk, I've tried to argue that we should also take the remaining steps in that direction. And I have tried to defend a theory in which meaning and grammar are autonomous parallel components. So both contribute information that's relevant for interpretation, which is integrated at the level of the discourse model. And using computational models and experiments, I have tried to show that such parallel architectures seem to be promising. They are plausible, they are explanatory, and they are predictive. So I want to just mention and thank all my junior collaborators here, students and postdocs, although as is often the case, one can only show some of their work in a given talk. So if you're interested in one of the big topics that I discussed here, composition, then please check out our theme issue for the philosophical transactions, which appeared last year, and which I co-edited with Andrea Martin, who gave a talk this morning. It's really full of interesting papers, several of them by other speakers at this workshop. So check it out. So thanks again, Peter, and the organization at the MPI, and thank you all for your attention.
Okay, thank you very much, Josue, for a very clear presentation of the model and the work that you have been doing.
I'm going to
again,
unshare.
Yes, very good. I'm going to give back again to Ashley for handling the moderating the discussion and questions.
Thanks, Peter, and thanks, Josue. I'm going to go very fast because we're running very short of time. We went a little bit over with the talk. So first, a question from a junior researcher, Bobby Chen, who says, thank you for an excellent talk. I really admire the beautiful architecture you proposed. ERP literature has shown some individual differences on language processing. For example, when reading same morphosyntactic errors, some people elicit N400 effect, aka negatively dominant group, whereas others elicit a P600 effect, aka positively dominant group. I'm wondering how your architecture can account for these individual variations. I think that's like Darren Tanner and Kyra Morgan-Short's work, probably.
Yeah, it doesn't account for them yet, but it, I think, would be able to accommodate situations in which processing of grammatical information is actually handed over to the M stream. And we are seeing examples of that in L2 acquisition, for example. We are seeing instances of that in grammatism. And I would not be surprised if there were individual differences that show similar patterns, and the parallel architecture can indeed accommodate situations where processing that in normal circumstances or in certain populations would go through one stream primarily, in other circumstances or in other populations, for a variety of reasons, would go through the other stream primarily. So I think it's part of the set of questions that I mentioned in my talk when I introduced the parallel architecture, about what kind of inputs and what kind of conditions determine whether processing for each particular input at each particular point in incremental processing of an input string would tilt the balance in favor of one stream or the other. But it's a great question, and I do think that we need architectures that have some built-in flexibility to account for findings of that kind, namely that should be able to accommodate the fact that in some cases, certain ERP effects are triggered, and in other cases or populations, other ERP effects are triggered. So hard architectures that assign ERP effects to fixed processing stages that the system has to obligatorily go through would probably not be on the right track, also because of those data.
Okay, thanks. Let's move on to the next question. This comes from Nina Kazanina. So an interesting dissociation between N400 for composed cut nouns versus LAN for composed cut verbs. Could you say a bit more about possible reasons for this dichotomy, including the fact that the N400 effect is a reduction while the LAN effect is an increase in amplitude? Is it specific to your study design, or have you seen signs of it in sufficiently similar previous studies? Thanks.
Yeah, so the dissociation is between N400 for composed nouns following adjectives and LAN for composed nouns following verbs. So we are measuring these two effects always at the noun. And that's important because we know that it's not the category of the eliciting word that's driving the effect, but it's the context in which composition happens. And indeed, the two effects could not be more different. So there are different components that are modulated, but also the direction of the effect is different. So when you can compose the noun in the context of the adjective, you get a reduction of the N400, and models of the N400 that associate the effect with pre-activation-like processes, I think, would be able to explain this effect. So it's because the noun receives more pre-activation from the context that you see a smaller N400 there. And this does not happen if there is a syntactic boundary in the cut condition. So the system knows that it cannot use any information that's available in the context for processing the noun. This is, of course, one possible explanation. And we have to look into these effects from cut compose paradigms that use different kinds of stimuli, but also different modality of presentation. Because in this first study, we show words visually without punctuation and without capitalization. So we are currently designing studies where we can look at the same in the auditory modality. It's only after we've collected data from those studies as well that we'll be able to get a better handle on what the N400 actually means in this case.
Okay, thanks. We have a question from Ryan Law. We're just going to try and get him up as a panelist to ask live. Is he here? Yes, he looks like he's here. There we go.
Hello. Yes, sorry, I was just rejoining. Thanks, Josue, for the talk. It was really interesting. I was wondering, in the context of the parallel architecture that you implemented in the Neuropsychology paper, is that an example of functional decomposition, sort of in a sense of Glennon and Bechtel and Abrahamson, and relatedly, do you think, to what extent do you think you also need to do like a structural decomposition?
Yeah, so thanks for the question. It's indeed a kind of functional decomposition. It's probably the wrong one in many ways. So note, for example, that the system now it's doing classification, and this is not what the brain is doing, although it happens to treat these sentences, for example, from the Kim and Osterhout study differently. So it appears to us as if it's doing classification, but we need to have versions of the model in which the task is different, in which the model is actually building models. So it's using the information that the parser spits out and that the neural network actually contains to build models. And then we need to start replacing the algorithms that we are using in each module with more plausible algorithms. For example, the constituency parser that we are using now is an incremental parser, but maybe we need to also allow for the possibility that the system will compute syntactic trees, so constituent structure. There's recent evidence that shows that different parts of the brain are actually sensitive to dependency and constituent structure work by Lopopolo, Willems, and others recent in neurobiology of language. So we need to find ways of taking neurobiological data and use it to build in the models that we construct, in the algorithmic level models that we construct, more and more plausible constraints and facts. And changing the algorithms is, I think, an obvious way to go. So one thing that we are exploring right now is to replace the syntactic parser and the neural network with two transformers. So we're going to have the same architecture, but effectively different algorithms that will produce the representations that will then have to be integrated and compared at the later stage. So the architecture, the parallelism between the two streams and the need to integrate their outputs at the later stage will stay. But to have a correct functional decomposition that helps us understand what happens in the mind and in the brain, we need to make those changes in the direction of more plausible algorithms.
Thank you.
Thanks. And I think we are out of time, so I'll hand back over to Peter.
I think in the interest of time, we now have to come to a closure of this session so far. Josue, thanks again for a very nice presentation. And I had a question myself, but I'll leave that for another occasion.